Hi, everyone. My name is Yana Pavlasic, and this is Lecture 11 for Robotics 102, Intro to AI and Programming. This is our second lecture about machine learning, and we're going to be talking about nearest neighbors today. So last time we talked about image classification, and we talked about how we could perform image classification using supervised learning, where we want to predict the class of some new image using a whole bunch of labeled images. So we talked about how machine learning algorithms generally tend to have two steps. The first step is the training step, where we want to learn a prediction model by optimizing over a bunch of labeled data. And then at test time, we want to actually use this model to predict the class of a new image. So we will split up our data so that most of our data is in our training set. So it's a bunch of labeled data that we're going to use to actually train our machine learning algorithm. And then the rest of our data will be kept in our test set, which is data that we'll use to actually test the accuracy of our machine learning algorithm and evaluate how good it is at doing image classification. So project 4 is a machine learning project where we're going to implement 3 different algorithms to classify images from the MNIST dataset, which consists of handwritten images of the numbers from 0 to 9. So we're going to implement nearest neighbors, linear classifier, and a neural network. This assignment is now released. The instructions are available on the project website. It's due on December 10th. The template code is also released. You can use the GitHub Classroom link to accept the assignment on GitHub. And this is it's linked on Slack in the normal place. And this is an assignment that's going to be done individually. So each student should accept this assignment. Okay, so today we're going to be talking about the first of the algorithms that we'll implement, which is nearest neighbors. So imagine that we have 60,000 labeled images of the type that we have in MNIST. How can we predict a class of a new image? So we're given this image. We can tell that this is the character 2, but how could we have our computer, how could we write an algorithm so that our computer can predict the class of this image? So one idea is that this image of a 2 might be numerically close to other images of 2s. So the idea of nearest neighbors is, given a new image, we want to find which image in our training sets our new image is closest to. And then we'll give this new test image the same label as the image in the training set. And that's how we'll say, and that's how we'll predict the label of a new image. So that's how our nearest neighbors algorithm is going to work. So that's project 4, part 1. You're going to implement this algorithm, and we're going to go through today what that implementation will look like. But you should get a result that looks something like this, where the algorithm is able to predict, find the nearest neighbor, and then predict a label. Okay, so so we said that we wanted to find the nearest image to some given test image, but what does nearest mean? So we need some way to define the distance between 2 images. So we're going to use a familiar distance function. We're going to use the Euclidean distance. So if we recall, when we did the Euclidean distance between 2 points or between 2 cells, we used the Pythagorean theorem to give us the distance. We basically just subtracted the x values and then the y values from each other. We took the difference between each dimension, squared them, summed them, and then take the square root. So we could do that in 2D. We did this in our other projects to find the distance in 2D. We can know that we can do this in 3D also. If we have 3D points with a z component, we can still take the difference in each dimension, take the square, add them up, take the square root, and that'll give us our distance in 3D. Well, so our image has many more than 3 dimensions. The image is 28 by 28 pixels, but we can just keep applying this same idea. We're going to do the Euclidean distance but in ND. So we can just, in each dimension, take the difference, square them, sum them all up, and then take the square root, and that'll give us our kind of n-dimensional Euclidean distance. So let's see what that looks like through an example. So we'll keep our formula here so that we can remember what we're trying to calculate. So how would we define the Euclidean distance between these two images? So these are tiny little 3 pixel by 3 pixel images. So we'll first take the difference between each pixel. So each pixel in A will subtract the corresponding pixel in B. So the next step is we'll square all of those, which will give us these values, a bunch of positive values, and then we will sum them all up together. So if we sum them all up together, this will give us 9. So that's actually our squared Euclidean distance. If we take the square root, then that gives us our final distance between A and B, which is 3. So they're about 3 units apart, whatever our pixel units are going to be. So we will define our Euclidean distance as this formula, and the nearest image will be whichever one has the smallest distance, defined this way. Okay, so we actually have a whole bunch of images to deal with in MNIST. We'll have thousands of them, tens of thousands of them. So we have many images. We're actually going to stack them all up. We can basically think of this as a list of matrices or a vector of matrices, but really when we're actually looking at them in Julia, this is going to give us a kind of 3D matrix. So Julia is going to see this as a matrix which is size n by width times height, where we have width times height of the image. So that's how we're going to get our images when we're working on our code in Julia. So this is a convenient representation, but also Julia likes to make things into these big matrices because computers are really good at dealing with matrices like this. They can do that really quickly using these different operations. So we'll learn a couple of ways that computers can do operations over matrices quickly a little bit later, especially when we're doing part 2 and 3. But for now, all you need to know is this is how the data is stored in MNIST. Okay, so back to nearest neighbors. Let's say we have some matrix of n training images. So we have n different training images in our MNIST, and we have some new test image that we want to classify. So we're going to call our images, our data, we'll call those X. So we'll have our X test and our X train. And then we also have our labels, which we'll call Y. So each of these training images has some label. And that label will be a number from 0 to 9, depending on what the actual image is. Okay, so if we have all these, how do we perform the nearest neighbors algorithm? Well, we already know that we can calculate the distance between different different images. So first, we're going to calculate the distance between our test image that we want to find a label for and every single one of our training images. We're going to calculate n different distances. So our nearest neighbor is going to be the smallest distance to the test image. So if we just took all of these distances and we took the minimum, we would get whatever the value of the smallest distance is. But we actually want to know which image is closest to our test image, not how close they are. So we can do that using what we call the argmin, which stands for the argument that minimizes these distances. So let's say our test image is closest to, for example, the train image number 7. Argmin is going to give us a 7. So it's going to say number 7 is the one that has the smallest distance. So that's the argument that minimizes distances. So then our predicted label is going to be whatever image number 7's label is. So we can go grab the 7th label from our vector of training labels, and that'll give us, and then we'll say that our test image has whatever the value of the 7th training label is. So let's look at a little example just to reinforce this. So let's say we have these 5 images. I didn't give them any numbers, but I gave them some labels. So they have these labels of just values from 1 to 3. So our goal is that we want to predict the test image label. So we have some test image and we want to say how are we going to classify this image? So first step is we want to calculate all of the distances between the test image and all 5 of the training images. So in this case, we only have 5 training images. So I went ahead and filled in a couple of different possible distance values here. So the minimum value here is going to be 0.07. So, and that minimum value corresponds to image number 4. So if we use our argument function over our distances, it's going to say number 4 is the closest image to X test. So that means that corresponds to this 4th image here, which has, so its nearest neighbor is this 4th image, and that has label 2. So we can go ahead and update the label of X test to be 2, the same as its nearest neighbor. So let's write this out in pseudocode based on our machine learning, our algorithm for a machine learning classifier. So at training time, all we are going to do is save our data, our X train and our Y train. We just need to save it. We're not doing any model fitting or anything at training time. So super fast training time. And then at testing time, when we give a new image and we say, what should the label of this neighbor of this image be? We're going to do the following. So for each of the for each test image that we're given, we are going to first initialize a distance vector. So here I'm just initializing the distances to 0. And then for every single training image, we're going to calculate the distance between our test image and our training image. And then we will find the nearest neighbor to our current test image. And then we will set our prediction to the same label of our nearest image in our training set. So we can do that for however many test images that we're given, and that's our nearest neighbor algorithm. So let's go through a small example of that. We'll do a little exercise. So if you're watching at home, you can pause here and try to go through this exercise and try to find classify this test image using the nearest neighbors algorithm, given these 3 training images. And I gave them labels here underneath them. So you can pause and try doing that at home, but I'll go ahead and go through the solution. Okay, so our distance from our test image to our image A, I went ahead and calculated that. I'm going to skip each individual step, but our final distance is going to be square root of 42, which is about 6.48. And then if we calculate the distance between our test image and image B, that'll give us 8.54. The distance between the test image and image C is 4. So the next step is we need to find the minimum. So the minimum distance is 4, which corresponds to image C. So our test image's nearest neighbor is image C, which means that we are going to give our test image the same label that C has, which in this case is 2. So in this case, the label for our test image would be 2. So that's our nearest neighbor algorithm in a nutshell. That's what you have to implement for project 4. So one thing that we haven't talked about yet is how do we know whether this algorithm is actually any good? So we can run in and do a bunch of different predictions, but how do we know how well our algorithm is doing? So your notebooks will include a calculation of the accuracy of your classifier. So the accuracy is just the percentage of correct classifications that the model made. So out of all the different test images that you gave, we'll give the algorithm a whole bunch of test images, and you want to count up how many that it guessed right. So then the accuracy will just be the number of correct predictions divided by the number of tests that you did. So you really want to make the number of tests as high as you can afford. So however many test images you have and however much time you can spare. So it'll take longer to run this algorithm on more images. So actually in project 4, you'll be able to play around with the number of training and testing images that you're using, because nearest neighbors is going to be pretty slow on the entire data set of 60,000 images. Imagine calculating the distance between 10,000 for all 10,000 images between each image and 60,000 training images. That'll take quite a while, but generally we want to use as many test images as we can. So the accuracy gives us a quick and easy to interpret measure of how good the prediction is. So 100% accuracy is the best we can do. 0% accuracy is the worst we can do. But what it doesn't tell us is how and why the algorithm fails, when it fails, and exactly what it's doing. So there are different types of evaluation that we can do as well. These are not included. These are not implemented for you in the notebooks, but I encourage you to try out calculating some different types of error like the ones that we're about to talk about, and you can implement those in new cells in your notebooks. So if we have a binary, let's say we have a binary classification problem where we can either classify something as true or false. So for example, a cat detector where we can classify something as a cat or as not a cat. So all of these elements on the green side are cats, and everything on the gray side are examples that are not cats. So this center image, let's say we have a classifier that predicts this center circle as cats. So all those ones are classified as cats. The ones outside the circle are classified as not cats. So there's different types of positives and negatives that we can get. So a true positive is a cat that is correctly classified as a cat. So it is a cat, we classified it as a cat, perfect, great. So we would count those that would be the number of correct predictions for our accuracy. So then we have our false positives, which we classified it as a cat, but it's actually not a cat. So this is a bird, we said it was a cat, that's wrong. So that's a false positive. A true negative are our other types of correct guesses. So these are images that are not cats, and we said they weren't cats, so we were right again. So again, those would also contribute to our number of correct predictions in our accuracy measure. And then we have our false negatives, which are cats, but we missed them. They were not classified as cats, even though they should have been. So those are different types of errors that we can get. So our accuracy is basically all of these green ones summed together and divided by the total. But we can calculate a couple more things about our classification algorithm as well. So first of all is precision, which basically tells us how valid our results are. So say that we have an algorithm where it's super important that anything that is classified as true is actually true, but we don't actually care if we miss some of them. Then we can, so precision gives us, what you want in these cases is high precision. So precision is the number of true positives divided by the number of true positives and false positives. So all of the ones that were actually guessed to be positive. Recall basically tells us how complete our results are. So if you want an algorithm that catches every single true case, but there might be some positives, then you want high recall. So an example of this, an example where you might want high precision is a search engine. So you want your search engine, you don't want to Google something and have irrelevant results shown in your front page, right? But if you miss some relevant ones, maybe we don't really mind so much because really I just wanted one answer. So as long as my page shows me some good answers, then that's kind of all that I want. If it missed a couple, then I don't mind too much. An example where we want high recall is in something like a cancer detection algorithm. So we talked about one example of image classification, which was melanoma detection. So would be really bad if our cancer detection algorithm gave us a false negative, right? So a false negative would be that someone actually did have cancer, but our algorithm said, you don't have cancer. So that would be really bad because that person would be in danger and we wouldn't have detected it. But if we have some false positives, that's actually not so bad. So if the algorithm says this is cancer, then the doctor can say, okay, well, we'll run some tests. And if it turns out it wasn't, that's okay. It's better to be safe than sorry. It's better to check. So depending on our application, what we actually want to do, we can decide, we can use these different metrics of precision, recall, accuracy. Sometimes it's helpful to present multiple different metrics. So we've been talking about this binary classification algorithm where we just detect something as a cat or not a cat, for example. Basically, if you want to calculate these types of metrics on data with multiple different classes like MNIST, which has 10 different classes, we can still do it. We basically just consider each classification a binary classification problem. So when we're classifying whether something is a 0 or not, we can basically, that's just kind of like 10 different binary classification problems where we could say, is this a 0 or not? Is this a 1 or not? Is this a 2 or not? Etc. So we can kind of extend this to multiple different classes by doing that. Okay, so when we specifically have lots of different classes, one helpful way to evaluate our classification, how well we're doing at classification is what we call a confusion matrix. So I've drawn so this is actually what a perfect classifier's confusion matrix would look like. And I'm actually drawing these confusion matrices for a different type of classification problem. Specifically, I'm using a small image data set called CFAR10, which has these different 10 classes. So airplane, automobile, bird, cat, deer, dog, car, deer, dog, frog, horse, ship, and truck. So it has these 10 different classes, and it's got a bunch of little images in each of these classes. So the perfect classifier's confusion matrix, if every single image is classified correctly, will look like this. It basically gives you a heat map of classification labels versus true labels. So here, all of the airplanes were classified as airplanes, all the automobiles were classified as automobiles, etc. So it is very unlikely that you get an absolutely perfect classifier like this. A slightly more realistic looking classifier might look something like this. So in this example, I had 100. This is an imaginary example that I made up, but I had 100 images in each of the categories. So along the rows, those are each of my true categories, and then along the columns are what they were predicted as. So in this first, in the top left corner here, I had 74 of my 100 airplanes, which were classified as airplanes. And then I had, if I move along my row, I had 2 airplanes classified, predicted to be automobiles, and then 18 airplanes predicted to be birds, etc. So I do that for each of my categories. For all of my airplanes, I check what I count up, how many of them were predicted to be airplanes, and then for each of the other classes. So what's nice about our confusion matrix is that it gives us more insight about our algorithm and what types of mistakes that it's making. So in this example here, we said that airplanes were, it looks like airplanes are doing a pretty good job of being classified, but there are a good number of them that are being, just by looking at this confusion matrix, I can see that there's a good number that were misclassified as birds. So that actually that gives us some useful insight. It kind of makes sense, you know, they're both flying things with 2 wings in the sky. So maybe if we're doing nearest neighbors, it kind of makes sense that some birds might be pretty close to pictures of airplanes. So we've misclassified those. So we could also kind of see which classes were doing a bad job of classifying. So here, deer are not being very well classified. There's a lot of deer being predicted to be dogs and horses. So again, that kind of makes sense, because you could kind of imagine that pictures of horses and dogs and deer might look kind of similar. So maybe your nearest neighbor's algorithm is mixing those up pretty often. So the confusion matrix kind of lets us be able to analyze our results in more detail than just a simple thing like just using accuracy. So again, this is just a made up example. This is not actually what the result that I got when I ran nearest neighbors, but it kind of gives us an insight of how we might analyze a confusion matrix. So you're free to try implementing a confusion matrix when you're classifying your images in nearest neighbors, and it will hopefully give you more insight into what the algorithm is doing. Okay, so now we know how to evaluate, how to implement nearest neighbors. We know how to calculate the distance between 2 images so that we know what so we have a definition of what nearest means. So our nearest neighbors algorithm will do pretty well, but can we do a little bit better? Well, the extension of nearest neighbors, there's an extension of nearest neighbors called k nearest neighbors. So if we want to make our algorithm a little bit more robust, we can let the k nearest neighbors vote on the label for our test image. So instead of just getting a new image and saying, well, what image is closest to this image, I can find the k closest neighbors. So in this case, I am finding the 10 nearest neighbors. This is the output that I got when I looked up the 10 nearest neighbors for each of these images up here. And then each of those neighbors can vote on what it thinks that image is, and then we'll use that to label the test image. So it's a k nearest neighbors algorithm. Basically what we've been talking about when we're talking about finding just the single nearest neighbor is called the 1 nearest neighbors algorithm. So the special case when k is equal to 1. And k nearest neighbors is an advanced extension for this assignment. So there is template code for you to implement k nearest neighbors. You can do so if you have time or if you'd like to for advanced extension points. So if we look at the example of the Most of these images would do pretty well if we did one nearest neighbors, but if we look at that last image there, the 9, the first nearest neighbor would actually be that 4 right there. So there are actually 3 4s that are close to the 9. I think, if I can read that handwriting correctly. And then there's 7 9s in the k nearest neighbors. So if we used one nearest neighbor, that 9 would get labeled as a 4, and that would be counted as an incorrect answer, an incorrect label. But if we used k nearest neighbors, where we used the 10 nearest neighbors to this number, we'd actually get 3 votes for 4 and 7 votes for 9, so it would get classified correctly as a 9. So we're actually doing a little bit better than our 1 nearest neighbors in this case. But one question that we need to kind of talk about is how we're going to pick that k. So with k nearest neighbors, we're basically changing what we call the decision boundaries. So let's say we have, this is a little example of some data that has 3 different classes: red, blue, or green. If we take a new data point that we want to classify, when we use one nearest neighbor, we get these decision boundaries in this middle image here. So basically, any point that we sample, if we put a point in a blue region, it'll be closest to one of the blue points, so it will be labeled as a blue. And if we put it in the green, any green region, it'll be labeled as green, etc. And so we can kind of see that if we look in our in this middle image, there's a couple points, like up here in the middle, there's this blue point in kind of an island of green. So if we get a point in anywhere in this blue region, it's going to be labeled as blue. But intuitively, it kind of like, this is in a pretty big sea of green. So maybe it's not a really, blue doesn't seem like a very good guess for a point in this region. And similarly, if we look at these little red points, and maybe those are just kind of outliers in our data. So if we do a 5 nearest neighbors classification, for example, then we get the decision boundaries in this image here on the right. So that will give us, so there are a couple of points here that we're considering. So for example, these little green points in this red zone, which we're going to kind of just consider outliers, and this whole region will be just considered a red region if we sample a new point. So what we're doing is, we're in this middle region, is we're kind of overfitting a little bit. So you can actually click on this link down here to play around with k nearest neighbors. So you can try changing what the k is and seeing what the decision boundaries are. But so we're going to talk a lot about overfitting and how to pick these numbers in this last module. But so what we call k a hyperparameter. So a hyperparameter is some parameter that we choose that isn't learned automatically by our algorithm. So in k nearest neighbors, k is a hyperparameter. Other examples of hyperparameters are actually, what model we're choosing. So choosing that the nearest neighbors as the model, or the data that we're choosing. And so generally we need to tune these parameters. So when we're picking, so for example, for k, we need to try lots of different k's and see which is the best performing one. So I want to talk a bit more about overfitting, because overfitting is a big problem in machine learning algorithms. Overfitting basically happens when we fit a model that corresponds too closely to our new data. So for example, let's say I have these points over here, just these 2D points, and I try to fit some polynomial to them. So for example, this blue line is a perfect fit for this data. Every single point in the data lies exactly on the blue line. But this is not a very good model. So, and why isn't it a very good model? Well, if I get a new point, so for example, this one here, then the label that I would give it, so let's say the x-axis is data, this is just data where with one dimension, and then the y-axis is the label. So if I were to guess, if I were to take this point over here, its label would be way up there because of this function that I've chosen. And that doesn't look like a very good guess. That's super far away from kind of the trend of the data, which we can kind of see just by looking at it, that it kind of lies along a line, right, with a little bit of noise. This is maybe a better guess for our data, right? So a linear fit looks more like that looks a bit like a better choice for our data. It is going, and that's basically going to avoid overfitting. But if we draw a line through our data, now our existing data points, there's going to be a bit of error between those data points and the line. But what we're going to gain is that we're going to do a better job at predicting on new data. So we're going to need to balance between how well we can fit our training data and how well we can predict on new data. So if we look at a classification example, because we're doing classification, let's say we're classifying points as either red or blue, and we've plotted them in 2D. Their values will be these 2D values, and their label is either red or blue. If we use this green line, so we draw this perfect green line to perfectly separate all the red data from the blue data, and then anything that falls on the red side of the green line will be classified as red, and on the blue side of the green line will be classified as blue. That is kind of an example of overfitting, right? If we have a new data point that's kind of near one of these blue points that lies more on the red side, we don't necessarily want to, it doesn't make a lot of sense to classify that as blue. So that would be what our one nearest neighbor algorithm would do. Probably a better fit is this black line, right? That kind of just these points along the boundary are just kind of going to be treated as maybe noisy outlier points, and we'll have a more smooth line. So a challenge in picking hyperparameters, picking machine learning models, and training them in general is the bias variance trade-off. So bias is error which is due to deviation from the true value. So if we're underfitting to our data, then we'll get more actual error in our true value. Variance is our error due to sensitivity and variations of the data. So if we change our data just a little bit, and then it gets classified differently, then we'll get high variance. So what we want to do is we want to have a classifier that has low variance and low bias. So we need to kind of trade, but we have to kind of trade off between both, because we're not going to be able to get perfect amounts of both. So if we have too much bias, we'll have underfitting, and if we have too much variance, we'll have overfitting. So we'll need to kind of trade off between these two and pick values that will do the best at classifying new data. So how do we do this? We've talked a lot about problems. We haven't talked about solutions. So let's look at a couple ideas for how we might actually tackle setting hyperparameters without overfitting or underfitting. So here's idea number one. We have our data set, a bunch of different labeled images. So for MNIST, we have 70,000 labeled images. So why don't we just pick the hyperparameters that work best on our data? So we'll just pick whatever value of k works the best. So in this case, we're minimizing what's called the training error. So the error of predicting our training set using our training set. So in this case, we're basically just memorizing our training data, and that's probably going to lead to overfitting. So that's actually not really a good idea. In fact, so our training error should be pretty low. Our training error is normally going to be lower when we test on our actual training data versus some new testing data. That should actually be lower than when we're testing on brand new data, because our model is optimized to work on our training data, because that's what we use to train it. So for nearest neighbors, k is equal to 1 should actually give us 0 training error, right? So if we take a training image and then we want to do prediction using our training sets, that training image is going to have distance 0 to itself in our training set. So we are always going, and so whenever we want to go do a prediction, it's going to be the closest to itself. So it's going to get predicted with its own label. So that'll give us 100% accuracy, 0 error. So that's kind of this nearest neighbors, one nearest neighbors is a great example of why this is a pretty bad idea. So if you did one nearest neighbors, you'd say, wow, my nearest neighbors algorithm is perfect. This is a great algorithm. I can get 100% prediction, but that's not necessarily true. So we've actually overfit here. So idea number 2 is we split up our data into train and test. So we'll use all of our training data, we'll evaluate on our testing data, and we'll pick whatever hyperparameter works best at classifying our test data. So that's a better idea. Here we're minimizing the testing error. So we'll pick whatever k gets the best testing error. That's a better idea. But we still don't really know how well we're going to do on brand new data that we've never seen, right? So when we were choosing the hyperparameters, we were choosing them to fit best on the testing data, but we don't have any data left over to test how well our k works on new data that it hasn't seen before. So maybe we've overfit to our testing set now. So this is actually the version splitting up into the training and testing set is how the notebook in your template code does it. But there's one other idea, which is a little bit better, which is that we're going to split up our data into, we're going to take our training data and we're going to cut out a little chunk of it. And that's going to be our validation error. So when we pick our hyperparameters, we are going to pick the hyperparameters, the k, like for example, the k that does the best at classifying the validation set given our training set. So then our testing set, we're going to use, we're going to pick our k. Once we've picked our k, we're going to lock that in and say that's our k. And then we will take our test set and we'll evaluate our test set using the hyperparameters that we chose. And then we can say, okay, this is a pretty good guess of how our algorithm will act in the wild. So if you take a brand new image, this is a pretty good guess of how good it will be. So that one is an even better idea than our last one, because it gives us a chance to see how our algorithm will actually do on unseen data. So there's another version of this, which we call cross-validation. So instead of splitting up our training data into training and validation just once, we can actually split our training data into, let's say, k equal folds. So in this case, 5 equal folds. And then we're going to run our whole algorithm on holding back 1 fold as the validation set. So using the first 4 chunks as training data and the 5th one as validation. And then we're going to do the same by holding out the 4th one as validation, and the same holding out the 3rd one as validation. And we'll pick whatever k does on average the best on all those different examples, and we're going to hold back the test separately. And then when we're done that completely, then we'll test when we've picked the best K that works, then we'll run it on the test set, and then we'll get a great idea of how well our algorithm does. So this is very useful to do in small data sets. It's not really used too frequently in deep learning just because it's very expensive and slow to do, because you'll have to, in nearest neighbors, we don't really have much of a training step. We just are saving our data. So in our training step, would be basically separating out these folds. But when we go on to algorithms that have more of a learning component, then that would mean we'd have to retrain our model on a bunch of different hyperparameters and a bunch of different folds. And that would be pretty expensive. So it's not used super frequently, but when we're doing nearest neighbors or K nearest neighbors, it's actually pretty feasible to do. So if you are implementing K nearest neighbors, or later on when we're training our linear classifier or our neural network, I do recommend, if you have time, trying out doing cross-validation to pick your hyperparameters. So this is actually going to be our best idea, and generally is going to give us our best hyperparameters that are the least likely to be overfit. Okay, so now we have talked about, so for project 4, we've talked about our nearest neighbors algorithm. Today, we talked about how to find the distance between images. We talked about how we could use that distance to perform the nearest neighbors algorithm and classify unseen images. And then we talked about how to actually evaluate our classification algorithms and what some best practices were for setting hyperparameters. That should give you everything that you need to know in order to go and implement part 1 of project 4, which is nearest neighbors, in your Julia notebooks. If you haven't yet, you can go check out the lab slides about Julia, and there's also an intro to Julia notebook, which will help you get used to Julia, and in class we'll have some supporting activities to help get used to Julia and working with images and matrices in Julia to do some of these operations. So that gives us our first algorithm. We have 2 more algorithms to cover. So the next lecture will be about linear classification, and that's what we'll talk about next time. So thanks everyone for your attention, and I'll see you next time.